Okay. Good afternoon, everybody. I'm very happy to welcome you to the second talk of today's afternoon session. Today we have this session. We have our speaker, uh, Kavitha Telikepalli. She is a professor at the School of Technology and Computer Science at TIFR Mumbai, and her research interest is in the broad area of graph algorithms and combinatorial optimization. In this two-part talk, the first part of which is today, she'll be talking about popular matchings and witnesses. And popular matchings have gained a lot of attention in the past mm, uh, decade or more, and we'll be learning about that from Kavita in today's and tomorrow's talk. So, without further ado, over to you, Kavita.
Thank you. Thank you so much, Meghna. And thanks so much to the organizers for this invitation and for organizing this workshop. It's been so good. Yeah, so my two talks are on popular matchings and their witnesses. So let's start. So I'll be covering some old work and some new work. So in the first half, I'll be doing some old work, but that will hopefully be a warm up for the newer part that will come later. So in the first half of the talk, we'll be looking at a bipartite graph where every vertex has a strict ranking of its neighbors, as in this graph here. So this is a very well-studied model in two-sided matching markets, and it has been used in several real-world applications, prominent among them being matching students to schools and colleges, doctors to hospitals, and so on. So one wants a good matching here, and the notion of goodness here is captured by stability. A matching is stable if there is no edge that blocks it. An edge AB blocks a matching M if both A and B prefer each other to the respective assignments in M. The matching on the left, the red matching is stable. It's easy to check that no edge blocks it. While the matching on right, the blue matching is unstable because the edge between the two middle vertices blocks it. So this is a very natural notion of optimality, and it has so many properties which has led to a lot of study of stable matchings and efficient algorithms for so many problems here. So let's start with the simplest questions. Does a stable matching always exist? Is it easy to find one? In their famous paper from 60 years ago, Gale and Shapley answered these questions, where they said, yes, their algorithm, which is a truly simple algorithm, finds a stable matching always. So this algorithm is essentially vertices in A propose and those in B dispose. Let's run it on this simple example. So the vertices in A, that is little a and s, propose, and the vertex B receives two proposals and B prefers S to A. So B rejects A's proposal and accepts S proposal, and A has no one else to propose to. T never even received a proposal, so we end with this, just the blue matching, which is a single edge. So in all applications, we want large matchings. There may be exponentially many stable matchings, but all of them have the same size. In fact, they match the same subset of vertices. And as we saw in this example, the size of a stable matching could be as low as half the size of a maximum matching. So forbidding blocking edges is a very strong restriction, and it hurts the size of the resulting matching. So some drawbacks of stability are size may not be so good, and perhaps the restriction that it should have no blocking edge is like too strong a restriction. So do we want to empower every edge with this veto power? So can we come up with a meaningful relaxation of stability that includes all stable matchings and shifts the focus from veto power to collective decision? So we want a decision that's made by the entire set of vertices as a whole rather than single edges blocking matchings. And more importantly, we also want to allow for the possibility of larger matchings, and that motivates popular matchings. So we said every vertex has a ranking of its neighbors that translates naturally into a ranking over all the matchings in the given graph. How does a vertex U compare to matchings M and N? So it just compares its assignments in both matchings, and it prefers the matching where it gets a better assignment, it is a better partner. And it is indifferent between two matchings if it gets the same partner in both. So let's compare any pair of matchings by holding a head-to-head election between them and ask every vertex, which of these two matchings do you prefer? Cast your vote for that. And in case you're indifferent between these two matchings, well, abstain from voting. And let's count the number of votes won by each of these two matchings. So let's check it on some examples. So let's compare the red and blue matchings. When we hold this head-to-head election between them, the top two vertices abstain from voting because they're indifferent between these two matchings. The two middle vertices vote for the red matching, and the two bottom vertices vote for the blue matching. So it's a tie. So we say matching M is at least as good as matching N if the number of votes it wins is at least the number of votes the rival matching wins. So red is at least as good as blue and vice versa. So let's compare the red and green matchings. Well, here the red matching wins the election. So the red matching is better than the green matching because it gets 4 votes. A matching that loses an election is not an interesting matching for us. So a popular matching is one that does not lose any election. A matching M is popular if M is at least as good as any matching. So let's use this function delta n comma m to measure the number of votes of n minus the number of votes for m. So it's a difference between the number of votes that n gets and m gets. And a matching is popular is exactly the same as saying delta n comma m is at most 0. So Garden-Force introduced the notion of popularity in matchings, where he observed that every stable matching is popular. It's a two-line proof. When we compare any stable matching with any rival, so if a vertex U prefers the rival matching to our stable matching, then its partner in the rival matching, N of U, has to prefer the stable matching to N. Otherwise, the edge between U and N of U would block the stable matching. But a stable matching has no blocking edges. So for every vote that N wins, there's a corresponding vote that S wins. So the number of votes for S is at least the number of votes for N. So I hope this is okay. So every stable matching is popular. Hence, popular matchings always exist because stable matchings always exist. So we are totally talking about bipartite graphs and strict preferences. So these were the properties we wanted, and popular matchings have already ticked the first 2 boxes. So they include all stable matchings, and by definition, they shift the focus from veto power to collective decision. And in fact, stable matchings are minimum size popular matchings. So we have indeed allowed for the possibility of larger matchings. We know there is an efficient algorithm to find a minimum size popular matching. That's the Gale-Shapley algorithm. Is there an efficient algorithm to find a max size popular matching? And in fact, if we want to say this is an alternative to stability, we would like an algorithm as simple as a Gale-Shapley algorithm. So let's be brave and ask the question, can we in fact adapt the Gale-Shapley algorithm to find a maximum size popular matching? So the definitions of stability and popularity seem quite different. Stability seems like a local property. Given a matching, it's very easy to test if it's stable or not. However, popularity seems to be a much more global property. We need to compare our matching against every matching. And in fact, given a matching, how do we test if it's popular or not? And we want a maximum size popular matching. So how do we show no larger matching is popular? So let's begin with this simple example where we ran the Gale-Shapley algorithm. So the maximum size matching here, the red matching, is a max size popular matching. We know running Gale-Shapley algorithm in this instance gives us the single edge SB, the middle edge. How do we adapt the Gale-Shapley algorithm to find the red matching instead? So can we come up with a new graph where that red matching is a stable matching? So in fact, let's think of this extremely simple transformation of G into a bidirected graph. Let's replace every edge UV with a pair of edges, one directed from U to V and the other directed from V to U. So for our small graph, the corresponding graph G prime is as shown here. So there are directions on every edge. And let's say every vertex prefers any outgoing edge to any incoming edge. So the preference order for any vertex is all its outgoing edges in the original order of preference, followed by all incoming edges in the original order of preference. So, so 1 is the top choice, 2 is the second choice, and so on. So if you look at the vertex B, its top choice was S, so its outgoing edge to S is its number 1 edge. Its outgoing edge to A is its number 2 edge. Its incoming edge from S is a number 3 edge, and incoming edge from A is its number 4 edge. So I've just listed the preference orders of A and B here. So the middle edge was a stable matching in the given graph. However, neither this red edge, the edge directed from S to B, nor the reverse edge directed from B to S, neither of them is stable in this bidirected graph. If we run the Gale-Shapley algorithm in this bidirected graph with preferences as given above, the matching we get is this green matching. And this maps to the matching we wanted to find. So let's just verify. Let's run Gale-Shapley algorithm in this bidirected graph. So both A and B propose along their top choice, that's an outgoing edge to B. And B receives edges along its rank 3 edge and rank 4 edge. And B prefers S proposal to A's proposal. That's a rank 3 edge. So it rejects A's proposal. Now A goes to its other edge, the edge incoming from B. And now B is getting a proposal along a rank 2 edge, and so it prefers A's proposal to S proposal. So it rejects S proposal, and S is forced to propose to its second most preferred edge, that is the edge leading to T. And yeah, that's the end of the algorithm. So we get indeed this green matching. So this was such a simple example. I hope this was clear.
So can I ask one question? So
Sure, please.
in this modified example, we can have a vertex appearing multiple times in the preference list of that vertex. Is that right?
Exactly, twice. That's why I put the superscripts just to differentiate. It's on edges, the ranks are there, not really on neighbors. So it looks upon each of, yeah. So A looks upon B in two avatars, one with a minus superscript, one with a plus superscript.
Yes.
So everyone is looked at in like two ways. One is you are the recipient, you're the other endpoint of my outgoing edge, and one is you're the other endpoint of my incoming edge. So it always likes B as a superscript minus vertex, like as the endpoint of an outgoing edge. So indeed.
Yeah.
And the preferences are on edges rather than on vertices. So otherwise, if we think of it as on vertices, it's a bit confusing. Now, B seems to be appearing in two places and so on. So let's think of it as on edges.
Sure.
Yeah, so this was such a simple example and it works here. Does it work in general? Yeah, so it does. So this is the max size popular matching algorithm in a bipartite graph with strict preferences. Let's construct the bidirected graph where I've just scribbled what I said. Outgoing edges are preferred to incoming edges, and among outgoing edges, it's the original preference order, similarly among incoming edges. Just run the Gale-Shapley algorithm in this bidirected graph. This gives us a matching M prime. In the bidirected graph, just delete those superscripts. So we get a matching in our starting graph. And the claim is this is a max size popular matching. That is, it is popular and any larger matching is unpopular. So we prove this via the notion of witnesses. So every popular matching has a succinct or compact witness of its popularity. So these were those superscripts that we, unceremoniously deleted as just some waste on top. Actually, that has a lot of meaning, and our matching has this witness of its popularity right there. And so, in fact, our algorithm found both a popular matching and a witness of its popularity. So our matching computed this, our algorithm, sorry, computed this green matching. And a witness for this is, so whichever vertex has a plus superscript, take its value. So I'm calling this witness alpha, take its alpha value to be +1, and the vertices that had a superscript of minus take their alpha values to be -1. So a witness for the green matching is given by alpha A and alpha T are -1, and alpha B and alpha S are +1. So what properties should this witness satisfy? The sum of all the alpha values should be 0, and every edge should be covered by the sum of alpha values of its endpoints. What does this sentence even mean? So given a matching M, let's define a corresponding edge weight function as shown here. Weight of an edge is just the sum of the votes of the endpoints of the edge for each other versus the respective assignments in M. And votes are just 0, +1, -1. +1 means V prefers U to U prime, and so on. So the weight of any edge is +2, -2, or 0. Is this definition okay? And it would be convenient to always deal with perfect matchings. So let's augment G with self loops. And any matching just becomes a perfect matching by just adding self loops at all unmatched vertices. And for any self loop, also we need to define its weight. And the weight of a self loop is either 0 or -1. It is 0 if M also left it unmatched, and it's -1 if M matched it to a neighbor. So the definition of this edge weight function was exactly to satisfy this property. For any matching N, if you look at the corresponding perfect matching N tilde, its weight is just this function delta N comma M. It is the difference between the number of votes that N wins and the number of votes that M wins. So M is popular if and only if every perfect matching has weight at most 0 under this edge weight function. So let's write the linear program for max weight perfect matching. It is the simple LP given here. So it's a perfect matching, basically also including self loops. So that's what the first constraint is saying for each vertex. And we want to find a max weight perfect matching under this edge weight function, weight subscript N. And M is popular if and only if the optimal value of this LP is 0. Let's write the dual LP. And these are the alpha values. So they are the dual LP variables. So we want to come up with an alpha value for each vertex such that every edge is covered by the sum of alpha values of its endpoints. That's what the first constraint is saying. Alpha A plus alpha B is at least weight of the edge AB. And we also get the constraints for self loops. Alpha U should be at least weight of the self loop at U. So subject to these constraints, we want to minimize the sum of all the alpha values. So M is popular if and only if there is a dual feasible solution alpha where the sum of all the alpha values is exactly 0. So this is a witness of popularity. And the matching M computed by our algorithm has the following witness. For each vertex U, if U plus is matched in our matching M, then its alpha value is +1. If U minus is matched in M prime, then the alpha value is -1. And if U is unmatched, its alpha value is 0. So every edge in our matching in the bidirected graph has a form A plus B minus or A minus B plus. So the sum of alpha values of every edge in our matching M is 0. So sum of all the alpha values is 0 because the unmatched vertices had alpha value 0. So we need to show it's dual feasible, and that follows quite easily from the stability of the matching M prime in the instance G prime. And we also need to show that alpha U is at least weight of the self loop. All these are easy to show. So the conclusion is the vector alpha as given by the superscripts is dual feasible, and in fact is dual optimal. Hence M is a popular matching in the given graph G.
Hey, Kavitha, can I ask a quick question?
Sure.
Yeah, so does it also speak to like popularity against fractional matchings? Like given that you're actually looking at, so it's not popular only among other integral matchings, but
True, but by Birkhoff von Neumann theorem,
okay,
every fractional matching is a
right,
convex combination of integral matchings. So if
right,
it's
right,
popular or integral matchings, it
got it.
naturally uh,
Yes, yes,
is
yeah.
popular fractional matchings as well. Indeed. Thanks.
So the witness is the dual optimality.
Exactly.
Okay,
Exactly. And there is a very simple witness with just 0, +1, -1 values. And
right.
but our algorithm was finding that too as the superscript. So
Uh-huh,
it just came to us for free, really. We didn't have to do anything. So Gale-Shapley algorithm gave us both the matching and its witness.
uh-huh. And does the Gale-Shapley itself have a primal dual interpretation?
Oh,
Not.
yes, in the
Oh,
sense. So if you look at this paper by Theo and Sethuraman, they prove the integrality of the. So you're right. It's not the Gale-Shapley algorithm, but there is some. Uh, so
uh,
basically, show the integrality of the stable matching Pareto formulation by Rothblum. So there is some kind of a self-dual property that it has.
oh,
There are some very nice properties, but I agree it's not Gale-Shapley as such, uh,
oh, okay.
but to
This,
prove that it has that is polytope, that a certain formulation is its polytope, it's an integral polytope and stable
uh,
matchings with extreme points. There are very simple proofs which use this LP and dual. So let me
uh-huh.
say that.
So
This
you can maximize like linear functions over the space of stable matchings and
absolutely, absolutely.
okay,
So in 92 itself, so we knew how to formulate the stable matching polytope. Indeed.
okay, great. Yeah, maybe 2 decades later. Yeah,
3 decades later.
3 decades. Yeah, thanks.
So please interrupt and ask me if there are any questions. So far, uh, I've shown that. So Gale-Shapley algorithm is itself, it's really the one ring to rule them all. So Gale-Shapley algorithm finds a min-size popular matching, that's a stable matching. In the bidirected graph, it finds a max-size popular matching, and the max-size popular matching indeed. And the superscripts of vertices give us the witness that prove that our matching is popular. And I'm yet to show no larger matching is popular. I'm at that spot now. So for any edge incident to an unmatched vertex, the alpha value of all unmatched vertices, that was 0. And while all its neighbors actually are matched, because our matching being stable in the bidirected graph has to be maximal as well. So, so if U is an unmatched vertex, every neighbor V of U is matched, and its alpha value has to be +1. So the edge UV is slack. The left-hand side sum of the alpha values is +1, and the weight of this edge is exactly 0. So our matching M itself is a primal optimal solution. Alpha is a dual optimal solution, and this edge is slack, which means any matching that contains this edge is less popular than M. It cannot be a primal optimal solution. That's a consequence of complementary slackness, which means any larger matching has to be defeated by M itself. Is this argument okay?
Yes.
Thanks. So it's all so quiet. Siddharth, you gave such a good talk. Everyone participated, and I'm giving a monologue. Almost no one is participating. So
I
yeah.
was talking about cake, so I guess that just enticed people.
Yeah, so any matching larger than M is unpopular because it has to contain a slack edge. Because its size is larger than that of M, it has to contain some edge incident to an unmatched vertex, and all such edges are slack. And so the matching M itself would defeat any larger matching, which means M is a max size popular matching. And finally, we have a better lower bound on the size of M than a stable matching had. It's easy to show that there is no length 3 augmenting path with respect to M. So if there is a length 3 augmenting path with respect to M, then it would contradict the stability of M prime in G prime. So we would basically have a blocking edge to this matching M prime. It's just the argument is what I've written here. If this is an augmenting path with respect to M, A, B, S, T, then either the outgoing edge from B or the outgoing edge from S would block the matching M prime. But M prime being a stable matching in G prime has no blocking edge, hence there is no such augmenting path, which means the size of M is at least 2/3 the size of any maximum matching is due to lack of length 3 augmenting paths. So we were unhappy that a stable matching had a guarantee of only half. A max size popular matching has a guarantee of 2/3. Am I halfway into the talk, Meghna?
Almost, yeah.
Okay, thanks.
You have 4 more minutes to go to halfway.
Okay.
Yeah.
So now I want to change the model a little. We'll move from the model of two-sided preferences to one-sided preferences. So here we are again given a bipartite graph, but it's only vertices on the left who we call agents that have preferences. Vertices in B are objects that are inanimate. They have no preferences. Such a graph is also called a house allocation instance because it arises in campus housing allocation in universities. So we want again a good matching here. So people have preferences over apartments. How do we allot apartments to various people and keep them all happy? The notion of popularity is relevant here as well. And in fact, popular matching algorithms were first studied in this model of one-sided preferences. So in this example, the blue matching is a popular matching. However, popular matchings need not always exist here. So this is a big difference from the strict two-sided preferences model. Here, by the way, we're allowed to have ties. Agents can have ties, like the agent A1 has 2 second choice neighbors. So we're allowing for ties. However, it's only one side that casts votes because only one side has preferences. So B basically has no preferences. And popular matchings need not always exist here. So let's look at this simple example with 3 agents and 3 objects. And every agent has the same preference order. B0 is the top choice, B1 is the second choice, and B2 is the third choice. The green matching is more popular than the blue one because 2 vertices, A1 and A2, prefer the green matching. So green matching gets 2 votes and the blue matching gets only 1 vote in their head-to-head election. The red matching is more popular than the green matching. And finally, the blue matching is more popular than the red matching. So we can have cycles and there's no popular matching here. The popular matching problem is, given such an instance, is there a popular matching? And if so, find one. So is there a nice characterization of popular matchings? So it's not difficult to show that. So let's call this edge set E1, the set of top edges. So these are the most preferred edges incident to agents. So if a matching M is popular, then M restricted to top edges has to be a maximum matching in this subgraph. So let's look at the subgraph. Let's call it G1, restricted to top edges. Any popular matching restricted to this subgraph has to be a maximum cardinality matching. But there could be other edges as well in a popular matching. Do we know what they are? So to begin with, let's add a dummy object as the last resort option, one such dummy object for every agent. So we can assume that all popular matchings are A perfect. And from now on, it's only A perfect matchings that are interesting to us. So for any agent, let's define these 2 sets, F of A, which is the set of A's top choice neighbors, and S of A, which is among non-critical vertices in this subgraph G1. Let's look at A's favorite neighbors. A vertex is non-critical if it's left unmatched in one or more maximum matchings. So a critical vertex is one that's matched in every maximum matching, and a non-critical vertex is not necessarily matched. So it's left unmatched in at least one maximum matching. So let's look at A's favorite neighbors among non-critical vertices in this subgraph G1. So a simple characterization of popular matchings was shown, in fact, it's not so many years ago now. So this is joint work with David Abraham, Rob Irving, and Kurt Wilhelm. So M is a popular matching in an instance with one-sided preferences if and only if M restricted to top edges is a maximum matching in this subgraph, and every agent has to be matched and its partner has to be either a vertex in f of A or a vertex in S of A. So every agent is matched either to one of its top neighbors or to one of its favorite neighbors. That's a non-critical vertex in the subgraph G1. So this immediately results in an efficient algorithm. So let's compute the set of edges E prime. E prime is a set of all those edges AB, where B belongs to f of A union S of A. So come up with this subgraph G prime. Find a maximum matching here. And if it's A perfect, return M. That's popular. That follows from the characterization. And if the subgraph has no A perfect matching, again, the characterization of popular matching tells us there's no popular matching here. So it's easy to identify non-critical objects. So that's what I try to write here. So let's take any maximum matching in that subgraph G1, and let's look at all vertices reachable by even length alternating paths with respect to M1 from an unmatched vertex. So that's exactly the set of non-critical vertices here. So in fact, the running time of this algorithm is exactly that order, that that's constant times the complexity of finding a maximum cardinality matching. So it's an order m square root 10 running time algorithm. Is this okay? So I went into the past 2007 or so because finally I'll come to some very recent work that is in a way closely related to this problem. So it's again one-sided preferences. We have a bipartite graph with one-sided preferences. Ties are allowed. But here we say cardinality is more important than popularity. So we somehow said stability was not so good with respect to cardinality, and that's how we motivated popularity. And now we're saying, well, even popularity is not giving us maximum cardinality matchings. Suppose cardinality is the most important attribute of a matching. That's more important than stability, popularity, everything. It's only maximum matchings that are interesting to us. Only those are feasible solutions. So what we want is a maximum matching such that there's no maximum matching that's more popular than our matching M. So M need not be popular. A smaller matching can defeat M. So there are many applications where the size of the matching found has to be is the most important attribute. So they include house allocation problems. Of course, you want everyone to get houses, assigning staff to hospitals in emergencies, and many others. So we always want a maximum matching in these applications. And among maximum matchings, we want a best one. So we seek popularity restricted to the set of maximum matchings. So a matching M such that no maximum matching defeats it. M is at least as good as all maximum matchings. So again, by adding some dummy agents and objects, we can assume without loss of generality that G has a perfect matching. So what we seek is a popular assignment. So the popular assignment problem is the following. Given a bipartite graph with one-sided preferences, is there a popular perfect matching, a popular assignment? If so, find one. So unlike the popular matching problem, we don't have a combinatorial characterization of popular matchings. So there we had a very clean characterization. We said every agent has to be matched to a neighbor in f of A union S of A. Here we have really no idea how does one characterize a popular assignment. So in fact, the first half of the talk where we talked about the max size popular matching, it was basically to familiarize you with witnesses. We'll use the LP method to solve this problem. And yeah, interestingly, the popular assignment problem is a generalization of the popular matching problem. Again, by assigning dummy agents and dummy objects appropriately, you can actually capture the popular matching problem as a special case of the popular assignment problem. So this is a more general problem. So let's see. Let's define an edge weight function in G as we did before in the first problem, where the weight of an edge is just A's vote for B versus his assignment in M. So it's +1 if A prefers B to its partner in M. It's -1 if A prefers its partner in M to B, 0 otherwise. So for any assignment, an assignment is nothing but a perfect matching. For any perfect matching n, its weight under this edge weight function, weight m, is just the difference between the number of votes that n gets and m gets, that is delta n comma m. So m is a popular assignment if and only if every perfect matching under this edge weight function has weight at most 0. So let's write the LP. I'm just mimicking what we did in that problem. So, but in that problem, we already had an algorithm and we're looking to prove its correctness. Here, we don't have an algorithm and we're trying to get ideas from witnesses in order to design an algorithm. So things were the other way around here. So let's write the LP for max weight assignment. That's what is given here. It's exactly what we saw before. It's only that the edge weight function is different here compared to there. It was +2, -2, 0, and also along self loops. Here, it's what was defined in the previous slide. So M is popular if and only if the optimal value of this LP is 0. Let's try the dual LP. The dual LP here is even simpler than earlier. Earlier, we had some extra constraints saying alpha u has to be at least weight of the self loop. Here, we don't even have those constraints. So the dual LP variables are the alpha values. Come up with alpha values, one alpha value for each vertex, so that every edge is covered, and minimize the sum of all the alpha values. So M is popular if and only if there is a dual feasible solution alpha whose sum of alpha values is 0. So we can in fact show that there is a nice looking dual feasible solution. So if M is popular, then in fact there is a dual feasible alpha such that the alpha values of all agents, so I'll call vertices in A agents, alpha values of agents are in the set 0, 1 till n minus 1, and alpha values of objects, so vertices in B are objects, so they are exactly the minuses of those values, 0, -1 till minus n minus 1. So the proof is not hard. It again follows from complementary slackness. For any edge in our matching M, we have tightness. And so in any constraint for an edge involving incident to B, I can replace alpha B with minus alpha A. And because the edge weights are in the set 0, +1, -1, it's easy to argue that for any two distinct consecutive values, alpha A and alpha A prime, it's enough to keep the difference to be 1. That's enough to cover all the edges. So there is a nice looking dual feasible solution. So the graph may not even have a popular assignment, but if it has a popular assignment, the popular assignment has a nice structured witness where the alpha values look as given here. So how do we use this to design an algorithm? So we don't have the algorithm. So let's interpret these alpha values as levels in a graph. So level 0, level 1, level 2, so on. So I want to come up with a subgraph of G and somewhat reduce the popular assignment problem to a perfect matching problem in that subgraph. So suppose somebody gives us a level function on the set of objects. So for every agent, let's define L star of A to be the highest level at which it has a neighbor. So L star of A is maximum of the levels at which any of A's neighbors sits in. So L is a function that's given to us on the set of objects. So let's consider the following subgraph G sub L. So what are the edges in this subgraph G sub L? For any agent, keep all its edges to its most favorite neighbors in the highest level. And let's look at one level below, in the level L star A minus 1. Let's keep A's edges to all its favorite neighbors in that level, provided these neighbors are preferred to all the top level neighbors. So for every most preferred neighbor B prime of A in level L star A minus 1, if A prefers B prime to all neighbors in the highest level, then keep this edge in this edge set. So let's do it on an example. So there are two agents here, A1, A2, and these numbers in the squares denote the levels of those respective objects. So there are two objects in level 0, one in level 1, one in level 2. And the numbers on edges denote preferences. So these 1, 1, 2, 1, 3, 2, they're all preferences of the corresponding agent. So L star A1 is 2 and L star A2 is 1. They are the highest levels at which these agents have neighbors. So note that A1's neighbor in level 1 is less preferred to its neighbor in the highest level, because its neighbor in level 1 is a rank 3 neighbor, and its level and its neighbor in the top level is a better neighbor, rank 2 neighbor. And moreover, its top choice neighbor is in level 0, which is 2 levels below the highest level. So neither of these dashed edges is allowed to be in our subgraph G sub L. And all the bold edges are in E sub L. Is this okay? So I'm defining this graph G sub L as shown in this example. So every agent keeps edges to its favorite neighbors in the highest level, and in highest level -1, if that neighbor is preferred to all the highest level neighbors, it keeps an edge. Otherwise, it doesn't.
And at the moment, we are assuming that the levels of B's are given to us.
Exactly. Indeed. We're assuming that if you are given such a level function, how do we build the corresponding subgraph G sub L? Exactly. So the claim is perfect match. Sorry.
Just one question. In this diagram, from A2's perspective, its most preferred partners are in level 0, right? So
That's
why
correct.
is that 2 marked edge, a dotted edge also? Why is it still in EL?
So it doesn't have any neighbors in level 2. So it only looks at its own neighbors. There may be other neighbors in level 2, but they're not its neighbors. I mean, it has no neighbors in level 2. Its highest level for a neighbor is level 1, and this is only one level below highest level.
Oh, right, that point. So if it's just one level, then you keep it. If it's 2 levels up, then okay.
Sorry. Exactly. So we are allowed to keep edges only to the highest 2 levels. Anything below, anything below that is not possible. Highest level, you always keep edges to your favorite neighbors. Highest -1, you keep edges provided they are better than your favorite neighbors in the highest level. So if M is a popular assignment, then in fact M is a perfect matching in this subgraph G sub L. And this level function then would be given by the witness actually. And conversely, if someone comes up with a level function and gives us a perfect matching in the subgraph G sub L, then in fact M is a popular assignment in the given graph. So basically our algorithm is, can we find a level function so that G sub L has a perfect matching? Then that's a popular assignment. So let's try to find a level function. Let's initialize the level of all objects to be 0 to begin with. And let's compute a maximum matching in the subgraph G sub L. If it's perfect, wonderful, return it. Else, increase the levels of all unmatched objects by 1. So that changes the subgraph G sub L. It gets updated. Go back to step 2. Compute again a maximum matching in the new updated subgraph G sub L. If it's perfect, job done. Else, increase the levels of all unmatched objects by 1. Go back to step 2. So eventually, either a perfect matching M in G sub L is returned, or the level of some object becomes N. In the former case, M is a popular matching, and we also get a witness along with it, and the witness is exactly given by levels. So alpha B will be minus of the level of B, and alpha A would be level of its partner. It's a perfect matching, so everybody has a partner. So alpha values for agents are just levels of their partners, and alpha values of objects are minus of their levels. And in the latter case, we show G has in fact no popular assignment. So it's not that we failed to find one, but actually G has no popular assignment. So this is our popular assignment algorithm. This is joint work with Thomas Kirai, Yannick Matuschke, Ildi Schlöter, and Ulrike Schmidt-Krippner. So this is the pseudocode of the algorithm. It's essentially what I wrote in the previous slide. So start with levels of all objects are 0. And while there is an object, while all objects are at level strictly less than n, construct the subgraph G sub L, compute a maximum matching. If it's perfect, job done. Else, for all unmatched objects, increase their level by 1. And so either we return a perfect matching or the level of some object becomes equal to n, in which case we return G has no popular assignment. So this can be solved in polynomial time, but it has a rather high running time. So we run the maximum cardinality matching algorithm n squared times. So its running time is m times n to the 5 over 2. I'll discuss all this in tomorrow's talk, prove the correctness of this algorithm. Right now, I'm just saying it as a black box. And an interesting open question is there a faster algorithm for this problem? So what happens when G has no popular assignment? So why don't we ask for an approximately popular matching? So how does one measure that? So a natural measure of the unpopularity of a matching is its margin. Mu of m is the unpopularity margin of m, which is defined as follows. It's the largest margin by which another assignment defeats m. And an assignment is popular if and only if its unpopularity margin is 0. So the K unpopularity margin problem is, given a bipartite graph with one-sided preferences, does it admit an assignment with unpopularity margin at most K? If so, find it. So we use the same method again. We come up with the same edge weights. And in fact, a matching, an assignment has unpopularity margin at most K, if and only if the optimal value of this LP is at most K. So it's exactly what we did for popular assignments, but instead of optimal value being 0, here I can only say, because it's the largest margin by which another assignment defeats it, and the optimal value of this LP is exactly that. It is max over all assignments n, delta n comma m, and the optimal value of this LP is at most K. It means m's unpopularity margin is at most K. Let's look at the dual, the same method. And so here we don't have as much structure as before. Earlier, the alpha values of agents were 0, 1 till n minus 1. Here I have some slack, it's n, but the alpha values of objects are 0, minus 1, minus 2 till minus n minus 1. So m has unpopularity margin at most k if and only if there exists a dual feasible alpha such that sum of all the alpha values is at most k, and in fact alphas have this structure. And so this algorithm is a little more detailed. It is not as simple as the previous one. So I'll just state it as a black box. I'll not really show the pseudocode of this algorithm. Our earlier algorithm can be extended to show an algorithm with running time m raised to k plus 1 times n to the 5 over 2 for the k unpopularity margin problem in G. So this is, of course, the dependence on k is exponential, which leads to the next question. Can we show an FPT algorithm for the K unpopularity margin problem? So to begin with, the K unpopularity margin problem is NP complete, even for strict preferences. And in fact, it's W1 hard. So it's very unlikely it has an FPT algorithm. In fact, we have a stronger lower bound. In fact, it's highly unlikely that it has an f of k times m to the little o of k running time algorithm. However, this assumes that the preferences are not strict. An open question is the K unpopularity margin problem in FPT with parameter K when preferences are strict? So we don't know the parameterized complexity of this problem for strict preferences. When preferences have ties, it's not likely to have one. So that's the end of my talk. So these are the references. The popular matching algorithm from 2007 is with these collaborators, and the popular assignment problem is with these collaborators. Thank you.
Thanks a lot, Kavitha, for the great talk.
Oh, thank you.
So maybe I'll ask if there are questions in the audience.
Hello, I'm audible.
Yes, yes,
Yeah, so I had one small doubt in that we were finding max size popular matchings.
sure,
We were building a graph with bidirectional edges and finding a stable matching in that. So
sure.
does it work so we were saying that any stable matching in G prime is a maximum popular matching in G.
Absolutely.
Does it work backward like every maximum matching in G is stable matching in G?
No, no, not really. It's a very good question, and it's not so. So
Hmm.
it's not the case that. So basically,
If I know it's for dominant matchings that work that way, right?
exactly. So
Okay.
it's basically those max size popular matchings that defeat all larger matchings that can be captured in this manner. That's exactly the class of dominant matchings.
Mhm.
So there can be max size popular matchings. They do not necessarily defeat all larger matchings. So they are not captured as stable matchings in this bidirected graph.
Yeah.
Exactly.
Thanks.
So I had a related question. So
Sure.
in this same model, we can compute amongst all the maximum cardinality matchings a popular matching, right?
That's right.
Does that algorithm also have a similar dual, uh, s- witness or something like that?
Yes, yes, indeed it does.
Okay.
Exactly.
And it
So
can,
Meghna's question is in two-sided preferences, right?
yes, two-sided preferences. Yes.
Exactly.
Yeah.
Exactly. So in fact, that work preceded this work. So that in fact gave me ideas. So the popular assignment problem, the machinery we use, everything actually was very much motivated by analogous work in for similar things uh, for, for
So that,
popular matchings within the set of maximum matchings in the two-sided case. Exactly.
yeah, yeah.
So yeah, so another open problem uh, is there a combinatorial characterization of popular assignments? So, of course, the LP method is very clean, but it's a very opaque method, right? We do not know really how a popular assignment looks like. Whereas a popular matching, we very nicely know that every agent has to be matched to a neighbor in F of A union S of A. Out here, this, so in fact, the LP method, it's so powerful, so useful, but it's very opaque. So that's my feeling that it would be nice to have a combinatorial characterization. So our algorithm is of course totally combinatorial. We're not solving any LPs in our algorithm. The algorithm is as simple as the pseudocode here. But
And it also has this similarity of keeping the edges of the topmost level and the second level. So
so
there,
here they're not really speaking the top choices. It's only the levels that indeed there is a similarity with popular matchings, but popular matchings are saying keep edges to your top choice objects. So in the highest level, it need not be your top choice object. You may not even have an edge to your top choice object, as in this example here. So here A1 doesn't even have an edge to its top choice object because it is in level 0. It's the levels here rather than its own ranks or preferences. But yes, it would be nice to have a combinatorial characterization of popular assignments. So though we can solve this problem, we don't really understand the structure of popular assignments. And that may lead to a faster algorithm for the problem.
So, quick question, maybe like a digression, but in general graphs, stable matchings don't exist, but even popular matchings might not exist.
Exactly, and that's an NP hard problem. So stable matchings, there is an efficient algorithm to decide if one exists or not.
Right.
There's in fact several efficient algorithms to decide. But for general graphs, uh, the existence problem is NP hard. So Sushmita and her collaborators showed this. We also showed it. Many of us showed it around the same time.
Okay. And so the other question is that so here you're using like a standard counting voting rule to determine but there are not an expert, but there are a lot of other voting methods. In particular, you could account for how good a preference is. Like use that as say a board account. Like you could use other voting mechanisms to like quote unquote rank matchings. So has that been considered? Or?
Oh yes, so Rohit, Vash, and I actually considered the Copeland's method, but they turn out to be even more intractable.
Oh, okay.
So in fact, because the set of matchings is exponentially large, right? So there are exponentially many candidates, and now to decide who is a winner, it's all very tough, very hard problems.
Okay. And does this the stability as a construct doesn't like naturally extend to other settings, but has there been work on looking at, for example, popular spanning trees and so on? So
Oh, yes, indeed. So there has been some work, but there were some hardness results, I think, on some popular spanning trees. But quite recently in 2020, with the same set of collaborators actually, Tamas
okay.
Yannick Madushke, Ildi Schlotter, and Ulrike, we looked at some problem called the popular branchings problem. So branchings are exactly our directed forests. So
Right.
we in fact gave a polynomial time algorithm to solve the popular branchings problem.
Okay.
So we said, in fact, popular branchings occur in liquid democracy. So we have to finally come up with a story to justify it, right? So, and for that, there was actually a story coming from computational social choice. So, in liquid democracy, if you want to transfer your votes, so the directed forest is basically capturing that. So, is
Okay.
there a way of transferring your vote so that it's a popular branching? And we had a polynomial time algorithm for that problem. That's also completely motivated by the LP method and witnesses and so on and so forth. So this method is actually quite powerful. So wherever we have a good understanding of the LP for the original problem, in this case, the LP for bipartite matchings,
Right.
understand, we take the dual, they form witnesses, and a popular structure in the case of branchings, a popular branching or a popular matching is a self-optimal solution. Its own incidence vector is an optimal solution of the primal LP. So that gives us lots of nice properties via complementary slackness. So I think Amit would have said his theme is going to be linear programming. So I'm already getting saturating people with linear programming. So it gives us so much power, and things follow quite nicely, but nonetheless it is opaque was my complaint. That's all. We don't really understand how solutions look like.
Yeah. Thank you.
Somewhat related question, like
Sure.
is there any work on the structural characterization of the set of popular matchings on the one-sided preferences?
On the set of popular matchings, it all follows from this combinatorial characterization, right? So, in fact, popular matchings, we understand them really well in one-sided preferences. So we know that every popular matching has this structure. So if you want to find a minimum cost popular matching, all you need to do is just optimize over these matchings. It's very easy to describe the set of all such popular matchings. Is it okay? So just write. So they can use only these edges. So any popular matching has to be A perfect. It has to match all the agents, and it has to use only these edges. So all these are very nicely captured by a linear program. And so you can describe the set of all popular matchings exactly as a set of feasible solutions of the linear program, and you can optimize over it. So for popular matchings, things are really well understood because of this combinatorial characterization. For popular assignments, we don't have such a characterization. That's what I was telling you.
Great. Thank you.
Thanks a lot once again, Kavitha.